there is a way to measure how advanced a civilization really is. It has nothing to do with weapons, or wealth, or even intelligence. It comes down to a single question: how much energy can you command? And by that measure, humanity is still a very young species, standing at the bottom of a very tall ladder. In 1964, a Soviet astronomer named Nikolai Kardashev proposed a scale, not for one nation, but for entire civilizations anywhere in the universe. He sorted them into 3 types, and the difference between each type is almost unimaginably vast. If that framing sounds abstract, remember that the whole story of human progress is, underneath, an energy story. For most of our existence, a single person commanded little more than the power of their own muscles. Then we tamed fire. Then the muscle of animals, and the push of wind and falling water. Then we learned to burn coal and oil, and at last to split the atom. Every great leap in what a human life could be, from the first farm to the modern city, was really a leap in the energy each of us could command. Kardashev simply took that ladder, the one we have been climbing since the first campfire, and extended it all the way to the stars. A Type 1 civilization can harness all the energy available on its home planet. Every ray of sunlight that strikes it, every wave, every wind, every drop of geothermal heat. The full power budget of an entire world captured and put to work. A Type 2 civilization does something far stranger. It captures the entire energy output of its star. Not the sliver of sunlight that reaches a planet, but all of it, the whole furnace, wrapped in structures that drink the star dry. Science fiction calls this a Dyson swarm. And a Type 3 civilization commands the energy of an entire galaxy. Hundreds of billions of stars harnessed at once. At that point, a civilization is less like a species and more like a force of nature. To feel how enormous these gaps really are, forget percentages and think in raw power. A single human body runs on roughly 100 watts, about the same as a bright light bulb. A large modern city runs on billions of watts. Our entire planetary civilization, right now, draws something on the order of 20 trillion watts. And then there is the sun, which pours out more energy every single second than our whole species has used in all of recorded history. The leap from where we stand to Type 2 is not a step, it is a chasm. That second rung even has a name and a father. In 1960, the physicist Freeman Dyson suggested that any civilization hungry enough for energy would eventually surround its own star with a swarm of collectors, capturing the sunlight that otherwise pours uselessly into empty space. He was not imagining a solid shell, but a cloud of countless separate structures, each one orbiting, each one drinking a little of the light. A star, slowly vanishing behind its own power grid. So where does humanity sit on this scale? The uncomfortable answer is that we have not even reached Type 1. Measured carefully, Earth today sits at around 0.7. We cannot yet capture the full energy of the single planet we are standing on. We are, in cosmic terms, barely getting started. Now most people file the Kardashev scale away as an interesting piece of trivia, but one man treats it as a to-do list. Elon Musk has said, more or less, that any self-respecting civilization should at least reach Type 2. And the company he built to get there is not the one you would expect. Because here is the strange part. SpaceX is not an energy company. It does not build solar panels. It does not build reactors. It builds rockets. So what could a rocket company possibly have to do with climbing an energy scale that stretches to the stars? The answer is the most important idea in this entire story. For decades, the thing standing between us and space was never a lack of ideas. Engineers have sketched orbital power stations and asteroid mines since the 1970s. The thing that killed every one of those dreams was a single, brutal number: the cost of getting 1 kilogram off the surface of this planet. For most of the space age, that number was catastrophic. On the space shuttle, putting a single kilogram into orbit cost tens of thousands of dollars. At that price, any structure large enough to capture real amounts of energy would cost more than the entire economy of the Earth. The math simply did not close. The ladder to the stars existed only on paper because no one could afford the first rung. What SpaceX did was attack that one number relentlessly for 20 years. And the weapon was reusability. A rocket that flies once and is thrown away is like an airliner you scrap after a single flight. A rocket that lands and flies again changes the entire equation. With the Falcon 9, the cost of reaching orbit fell not by a little, but by roughly an order of magnitude. When the first Falcon 9 booster came back and touched down upright on a landing pad in 2015, it looked to most people like a special effect run in reverse. But it was, quietly, one of the most important economic events in the history of spaceflight. A machine that had always been thrown away had, for the first time, flown to the edge of space and then come home to fly again. The disposable era of rocketry was over, and almost nobody outside the industry noticed. And Starship is designed to finish the job. A fully reusable rocket, the largest flying machine ever built, engineered to carry more than 100 tons to orbit and then come home and do it again. If it works at scale, the cost per kilogram could fall by another order of magnitude into a range that would have looked like fantasy a generation ago. This is the quiet revolution. Not a destination, but a price. Because once the price of reaching space collapses, everything that was impossible becomes merely difficult. And SpaceX has already made its first move on the energy scale itself. In early 2026, the company filed with regulators for permission to launch a constellation of up to 1 million satellites. Read that number again. 1 million. And the detail that matters most is the orbit. The plan places these satellites in sun-synchronous paths, orbits chosen, so the spacecraft stay bathed in sunlight for as much of the time as possible. Officially, it is described as an orbital data center. But look at what it really is. A vast array of solar collectors in space, gathering sunlight that never sets. It is, in Musk's own framing, humanity's first real attempt at harvesting energy on the scale of a star. And this is the key to SpaceX's true role. SpaceX is not the thing that captures the energy. SpaceX is the ladder. By collapsing the cost of reaching space, it makes energy at astronomical scale affordable for the very first time. It builds the rungs. And once the ladder exists, other companies can begin to climb. So let us meet 5 of the climbers. The first climber does not go to space at all. It stays right here, and its job is to finish Type 1. Tesla, the sister company, is building the machinery to capture Earth's own star from the ground. Solar panels to gather the sunlight that strikes us, and enormous grid-scale batteries, the megapacks, to store it and smooth it out. On its own, this is just a clean energy business. But seen through the Kardashev lens, it is something bigger. It is an attempt to weave an entire planet's sunlight into a single, usable web. The first, unglamorous rung of the ladder. The second climber is chasing something humanity has wanted since we first understood the night sky: to build a star on Earth. Commonwealth Fusion Systems is one of a handful of companies racing to make nuclear fusion, the reaction that powers the sun, work inside a machine. It has raised around $4 billion, and its experimental reactor called SpaceX's is targeting the moment of scientific break-even, where the reaction gives back more energy than it takes to start. A first commercial plant producing hundreds of megawatts is aimed at the early 2030s. A rival, Helion, has already signed the world's first deal to sell fusion electricity to Microsoft, targeting 2028. If any of them succeed, the ceiling on human energy lifts almost overnight. The third climber takes the idea of solar power and lifts it off the ground entirely. Etherflux, founded by one of the co-founders of the trading app Robinhood, is building satellites that gather sunlight in orbit, where there are no clouds and no night, and then beam that power down to Earth using lasers. It has raised around $60 million and is aiming for its first demonstration in space. If space-based solar power works, it turns the sky itself into a power plant. The fourth climber is stranger still. Reflect Orbital wants to put a fleet of enormous mirrors into orbit and use them to catch sunlight and reflect it back down onto solar farms after the sun has set. It is early, and it is audacious, and it is exactly the kind of idea that only becomes thinkable once launch is cheap. It is a civilization beginning to move sunlight around on purpose. And the fifth climber goes looking for the raw material to build all the rest. Astroforge is chasing asteroid mining, the extraction of precious metals like platinum from the small worlds drifting between the planets. This sounds like the most distant fantasy of the five, but it points at something essential. Because if you ever want to build energy structures on the scale of Type 2, you cannot lift the material up from Earth. There is not enough, and it costs too much. You have to build in space, from space. Astroforge is a first tentative reach toward the supply chain of a spacefaring civilization. Look at those 5 climbers together, and a shape appears. It begins on the ground, weaving a planet's sunlight into a grid. It reaches for the power of the star itself in a reactor. It climbs into orbit to gather sunlight where it never fades and to bend that light back toward home. And finally, it pushes out into the asteroids for the raw material to build bigger still. Earth, then orbit, then deep space. Each rung commands more energy than the last. And under every one of them is the same ladder, the collapsing cost of flight that SpaceX set in motion. And it is worth pausing on what even the first rung would mean, because Type 1 is not a science fiction trophy. A civilization that truly captured its own planet's energy would have no energy scarcity anywhere on Earth. Enough power to pull carbon back out of the sky, to turn seawater into fresh water at will, to lift every single human being out of energy poverty. Before the stars, before the Dyson swarm, that is the price sitting on the very first step. That alone would be the greatest achievement in our history. But now, the honest part, because a story like this can very easily become a fairy tale. We are not on the verge of a Type 2 civilization. We are not even Type 1. That figure, 0.7, has a long hard way to go, and closing it will take decades at best. And the scale of Type 2 is almost impossible to overstate. To truly wrap a star and drink its full output, you would need more raw material than exists in the entire asteroid belt combined. As the astronomer Jason Wright has pointed out, a real Dyson swarm is not a construction project. It is closer to dismantling a planet. The million satellites SpaceX has proposed are, against that backdrop, a single grain of sand on a very long beach. And every company we just met is a bet, not a certainty. Fusion has been 20 years away for 70 years. Space-based solar power has never been done at commercial scale. Asteroid mining has returned, so far, essentially nothing. Any one of these could fail entirely, and the timelines they promise should be read as hopes, not facts. And yet, something real has changed, and it is worth naming clearly. For the whole of human history, the ladder to the stars was blocked at the very first rung by the cost of flight. That block is now lifting. SpaceX did not build the Dyson swarm. It did not capture the sun. What it did was quietly change the price of the climb, and in doing so, it turned a set of impossible dreams into merely difficult engineering problems. That is the real role SpaceX is playing. Not the energy, but the axis. Not the summit, but the ladder. For the first time in the history of our species, the rungs are being laid, one launch at a time. Think about what that actually means. Every prophet of a spacefaring future for 100 years ran into the same invisible wall. The physics was fine. The engineering was hard but possible. The problem was always the bill. And the rocket company, of all things, is the one that finally started tearing that wall down, not with a new source of energy, but with a lower price on the way to reach it. So the ladder now exists, and a handful of companies have started to climb. Whether we reach the second rung, and how far beyond it we go, is no longer really a question of physics. It is a question of will and of time, and of whether a young species can hold a goal steady across generations. The scale has always been there, indifferent, waiting. What has changed in our lifetime is that we have finally stopped merely looking up at it and started to build the first few steps.